Hello teacher, I'm S. Chambla. Today I'm going to show you my Java Homework 10 and let's start. Firstly, I use import Java util and we use Java util for queue, iterators and etc. And after that I created an binary tree and its public class. It extends comparable. It is generic binary tree storing comparable elements, and after that we have basic node structures in there. Private static class node it's meaning static, so it doesn't capture outer instance, and we have e data in here and its elements stored in the node, and node e left and right, it's pointers to children, and we have node constructor in there, node data, and we save data reference, this data equal to data, and we have tree field and constructor in there, private node e root with we pointer to the tree root, and null means to empty, and public binary tree, it's empty constructor and it's empty tree. And after that we have simple binary search tree inserts in there. It's public void insert a value, it's public helper to the grow the tree, and root equal to insert rec root and value. It's delegate to recursive method, and after that private node e insert rec node e and ev. It's an classic binary search tree insertion, and if not equal to null, it's return the new nodes. When empty spot found, it's meaning that it's new leaf, and integer compare, we compare to node data. It's compare new value with current nodes, and if comparement lower than 0, not left equal to insert rec not left and v, and it's recurs left, and else if comparable compare bigger than 0, it's not right equal to insert rec not right v, and it's recurs right. And after that it's duplicates ignored in there, and equal elements meaning to do nothing. And after that we have return node in there, it's return unchanged or updated subtree root. When we discuss insert time complexity in there, it's equal to OH, and when we discuss to space complexity, it is equal to OH2, because standard binary search trees insert traverses the one route to leaf paths, so it's the OH, and after that we have level order iterator in there. It implements iterator, it's breadth first iterator, and private final q not e q equal to new array the q, it's first in first out q holds frontier, and we have level order iterator, not e start in there, its constructor takes root reference in there, and if start doesn't equal to null, q offer start, and non-empty tree is equal to enq root, and after that when we discuss to level order iterator time complexity or space complexity, both are equal to O1 because it just places the roots into the queue, so it's O1 O1. And when we discuss to has next in there, public boolean has next, we have boolean condition there. It's true while queue not empty, and its return queue is empty. And after that we have public e next in there. I'm sorry, discuss to when we discuss the has next time complexity, we will see O1 because it is an a simple is empty check. So is empty check is time complexity is O1, and has next time complexity is O1 too. And when we discuss the next uh, public e next, it's deliver the next element in the breadth first order, and if has next is throw new no such element exception, and uh, it is an safety check, and not e current equal to q pole. It is an pop front node, and if our current left doesn't equal to null and q offer current left, and if current right doesn't equal to null and q offer current right, it's in there in current left, meaning the enqueue left child if exists, and we have cur right in there, and it's enqueue right child if exists, and we have return cur data in here, and its current data in here, and its return element stored and its current node, and we have public void remove in there. It's I'm sorry, when we discuss the I forgot everything every time. Uh, when we discuss next time complexity is O1 amortized, and when we space complexity in there, it's OW because the Q and Q each node once, so total cost over n nodes, and auxiliary space equals to the maximum width. So space complexity is OV, OW, and time complexity is O1 amortized. And we have remove comment in there. It is a optional op not supported. So we can explain with the it is a classic remove method. So in there we have public accessor in there, get level order iterator, public iteratory, get level order iterator, its factory methods demanded in tasks, and return new level order iterator route. It's wrap the current routes in iterators, and we defined and we define an binary tree in there, and after that we create a demo for our tree demo in there. Uh, when we discuss the tree demo Java, but first of all I will discuss time complexities get level order iterator, so I forgot it, and now I discuss its time complexity. Uh, its time complexity is O1, and space complexity is O1 too, because it is an single object creation, so it's O1 O1. When we look out our tree demo, uh, we have Java. We import the Java util iterator in there, and we have public class tree demo in there. It's a public static void main string, and it is an entry point. And binary tree integer, t new binary tree is creates empty tree of integers, and we build an tiny binary search tree in there. uh, I give them uh, I didn't write like lower to the bigger type. I write the numbers randomly, like 50, 70, 30, and 20. So our binary search tree is uh, it will be right lower to the bigger, not lower to the bigger. Uh, left is lower type, typical binary search tree type with numbers, and we have integer values in there. And for integer values, we insert v, and we print nodes in level order. It will be right level order type in there. It doesn't level order type in there, but when we start the demo, it will be print nodes in level order, and we have level order is equal to and iterator integer equal to get level order iterator, while it has next system out print it next blah blah and system out print. When I start my demo, uh, so you see 50 is my root, and after that it see 70 and 30 in there, and it writes to it prints to 30 to left. So lower to the left type is the typical binary search tree definition. It's 30 to left, and after that it has two more nodes, 20 and 40. So 20 is lower, and uh, it's right. It prints the 20 to left and 40 to right. After that, it has to again two nodes, 80 and 60. So it prints to 60 to the left and 80 to the right, because again 60 is lower, and it's the typical binary search tree effect. And this week I defined the binary search tree, and we did it to 3 demo teachers. Thank you for listening. See you next week.